Welcome to this explainer. Okay, today we're cracking open what is essentially a high-stakes microbial detective manual. We're looking at the EUCAST guidelines for the detection of resistance mechanisms. Now, if you track infectious diseases or clinical microbiology at all, you already know that identifying exactly how a bacterium is evading our best drugs isn't just some academic exercise. It is absolutely critical for infection control and public health. So we are going to unpack exactly how laboratories hunt down the most dangerous superbugs using these highly precise guidelines.
Here's how we're going to break this down. First, the antibiotic resistance threat. 2, understanding CPE and ESBL. 3, initial screening for resistance. 4, phenotypic confirmation tests. And finally, rapid biochemical detection methods. Let's get right into it.
Section 1. The antibiotic resistance threat, the real-world stakes.
Take a look at this number, 62%. It's honestly staggering. According to the source data from the European Antimicrobial Resistance Surveillance Network referenced in the guidelines, roughly 62% of invasive Klebsiella pneumoniae isolates over in Greece are completely non-susceptible to carbapenems. And Italy? They're sitting right around 33%. So, we aren't just talking about some theoretical what-if scenario here. We are looking at a severe, right-now epidemiological reality. These bugs are spreading like wildfire, making these guidelines our literal frontline defense to catch them before they spark unchecked outbreaks in our hospitals.
Moving on to Section 2, Understanding CPE and ESBL, the prime suspects. So our prime suspects here are essentially defined by their weapons, specifically which crucial antibiotics they can completely dismantle or hydrolyze. Now, CPEs, these are your heavy hitters. They produce enzymes that just wipe out penicillins, most cephalosporins, and, crucially, carbapenems, which, as we know, are often our absolute last resort drugs. ESBLs, on the other hand, produce enzymes that can destroy penicillins and cephalosporins. Yeah, even those critical third and fourth generation ones. But here's the kicker. They do not hydrolyze carbapenems. Figuring out exactly which weapon the bacteria is holding? Well, that's the whole point of the EUCAST testing strategy.
All right, Section 3. Initial screening for resistance, finding the tripwires.
For laboratory scientists, the workflow actually relies on this really elegant 3-step algorithm. Step 1 is just your standard routine susceptibility testing, the usual clinical profiling. But Step 2 is where the EUCAST guidelines actually kick into high gear, applying highly specific screening cutoffs. If a sample trips those alarms, boom, we immediately move to Step 3, which is performing definitive phenotypic confirmation. Let's take a closer look at what those cutoffs actually look like.
When we're hunting for carbapenemase producers, the guidelines highlight this super fascinating diagnostic trade-off between two drugs, meropenem and ertapenem. Meropenem absolutely hits the sweet spot. It's the best balance of sensitivity and specificity. Basically, an MIC greater than 0.125 milligrams per liter or a zone diameter less than 28 millimeters and your alarm bells should be ringing. Ertapenem, on the flip side, is actually the most sensitive carbapenem. It'll catch pretty much everything, but its specificity is pretty low because it's kind of unstable. Bacteria that just have an ESBL combined with, say, simple porin loss might actually show up as resistant to ertapenem. That gives you a false alarm for carbapenemase. So meropenem, definitely the go-to screening agent here.
Now, if we pivot and screen for ESBL specifically, the tripwire changes. The guidelines tell us to use indicator oxymenocephalosporins. To get specific, an MIC greater than 1 milligram per liter for either cefotaxime, ceftriaxone, or ceftazidime. That is your threshold. Hit that, and it absolutely demands further investigation to confirm ESBL production.
Which brings us to Section 4, phenotypic confirmation tests, the interrogation phase. This algorithm beautifully maps out the step-by-step logic of synergy testing. Think of it like a biological interrogation. Once a sample gets flagged, scientists use combination DIS testing. They essentially expose the bacteria to a carbapenem, like meropenem, both on its own and then mixed with specific chemical inhibitors. By watching closely to see which inhibitor actually restores the antibiotic's ability to kill the bacteria, a process we call synergy, the lab can perfectly map out the exact resistance profile.
And here is the breakdown of those interrogation tools. If tossing in boronic acid creates synergy, your suspect is a Class A carbapenemase, like KPC. If dipicolinic acid, or EDTA, does the trick, you are looking at a Class B metallo-beta-lactamase, or MBL. Cloxilin, we use that to isolate AMP-C enzymes. But check out OXA48, a Class D enzyme, At the time these guidelines were written, there actually weren't any commercially available inhibitors for OXA48 on standard panels. Crazy, right? So labs had to rely on a totally different clue: high-level resistance to temacillin, specifically an MIC over 128. That acts as a massive red flag, a really strong phenotypic marker for OXA48-like enzymes.
Okay, let's speed things up in Section 5. Rapid biochemical detection methods, accelerating the verdicts.
Since standard combination disc testing takes a while, let's do a rapid-fire rundown of the biochemical and physical assays that save crucial diagnostic hours. We've got colorimetric tests like the Carba-NP, the blue Carba, and the beta Carba test. There's the carbapenem inactivation method, though to be fair, that one still takes overnight. But then we get into the truly sci-fi stuff: Mal-Ditoff mass spectrometry and these ultra-fast lateral flow assays.
The real magic here is how these tests make the invisible, well, visible and fast. Take the Carba-NP test, for instance. It detects the actual physical hydrolysis of the carbapenem drug. When the bacterial enzyme destroys the antibiotic, it shifts the pH of the solution. That triggers a visual color change in a phenol red indicator, going straight from red to yellow. The whole thing takes under 2 hours. It's just this incredibly elegant, totally simple visual confirmation that, yep, a dangerous superbug is in the room. If we want to get even more advanced, we look at Mal-Ditoff mass spectrometry. This machine literally measures the physical disappearance of specific carbapenem mass spectrum peaks in real time as the bacteria digest the drug. You get results in under 30 minutes. And then there's the new frontier: lateral flow assays. These use colloidal gold nanoparticles bound to a membrane to immunologically capture specific epitopes of enzymes, like our tricky OXA48. Honestly, it functions a lot like a rapid pregnancy test, but, for superbugs. And it delivers a highly specific verdict in about 4 minutes. 4 minutes! That is a real game changer.
Okay, we've gone pretty deep into the lab techniques today, from indicator cephalosporins to mass spectroscopy. But let's zoom out for a second and ask, why does identifying the exact resistance mechanism matter so much? Why not just slap a resistant label on it and call it a day? Well, because these microscopic verdicts completely drive macroscopic, life-saving decisions. Knowing if a bug produces a very specific carbapenemase dictates exact isolation protocols in a hospital. It informs regional public health tracking. It stops outbreaks from crossing international borders. Simply put, the specific mechanism dictates the specific response.
We'll leave you with this genuinely stark reminder straight from the EUCAST text. These enzymes, they don't just stay put. The genes encoding them are sitting on transposable elements on plasmids, which means they are readily, easily transferable between different bacteria. We are quite literally witnessing a real-time, ongoing evolutionary arms race playing out right inside our hospitals. By standardizing exactly how we detect these mechanisms, guidelines like EUCAST give us a fighting chance to stay just one step ahead. So the next time you hear a news story about antibiotic resistance, ask yourself, are we deploying the right diagnostic tools fast enough to actually catch it?